Welcome. Today we will be taking a look at the notes worksheet entitled The Dot Product. And this represents just one last operation dealing with vectors and its connection to trigonometry. So we'll go ahead and start this out right away with an example at the top of your page and then kind of define a few things and again see its connection to trig as we go through the process here. So let's do the example one at the top. I just have two vectors represented algebraically. So the first one, v is equal to negative 4i plus 3j. And then a second one, w is equal to 8i minus 1j. And so these are just operations that you can perform on vectors. And in this case, this is the one we've done before. So as a matter of fact, let's go ahead and put a little asterisk next to letter A. But basically, we would find the resultant of the two, the sum of the two. And so in this case, remember the nice thing about this, when we're in this AI plus BJ form, it's just combining the like terms. Combine the horizontals and then combine the verticals. So without too much issue here, it looks like we would have a 4i and it looks like a plus 2j. And we have done this before, of course, and we've seen it graphically and really not the priority of today's lesson. Other operations that you can kind of do with vectors, we haven't talked about when you had the resultant and you were kind of decomposing it, kind of having one original and getting the other, but maybe that would be the context for subtracting. But basically it's the same thing there. And so you basically would take just combining the horizontals and the verticals, this minus this, so negative 4i minus 8i, so I'm getting a minus 12i or a negative 12i, and then 3j minus negative 1j. So how about something like this? And again, we haven't seen a context for doing what is called scalar multiplication, but that would be this case right here, just taking both the horizontal and vertical components and multiplying it by a factor, essentially of 4. In this case, you would change the size of each part by that factor. In this case, I'm hoping, again, not because it's a priority for us by any means, but you would just multiply each of the a and b values by 4, so you'd get negative 16i. And 12j. Now just one thing to notice, and really the only reason I put this example on this notes worksheet, is when we perform these operations, addition, subtraction, and what's called scalar multiplication, we end up getting a vector as an answer. Everyone okay with that piece? We get a vector as an answer in AI plus BJ form. Now the operation that we're going to do today, and of course product, by the way, does mean multiplication, so we are going to perform some type of multiplication on vectors, but as it says on your paper, unlike the previous operations, the dot product does not produce a vector, everybody. In fact, if you can underline that for me, the dot product produces just a numerical value. And so let's go ahead and define that piece and then kind of take a look at it. So it says on your paper, the dot product of two vectors, and here's what I have. If you can kind of write it with me, that would be great. So if I have two vectors, I'll call the first one v. So it's going to have an a and a b, so I'm going to try to do a little sub 1 right there. And the b also, sub 1, so something like that. So if v is equal to that, and w is equal to another one with another a and b, so ai and bj, of course, just like we've been representing algebraically now. Very simply, then, when we multiply them and get what is called the dot product, so this would be v times w, very simply we take the horizontal components, the a's, and we multiply them together. So a1 times a2, and add that to the vertical components multiplied together, the product of those. So b1 times b2. And so that's our calculation at hand today. So again, we multiply the two a's, we multiply the two b's, and because these are all real numbers, when you get a sum, obviously, it stays as just a real number. So again, really not too bad here. You're going to get the hang of this in no time. Let's go ahead and just kind of reinforce it with an example here, of course. So example 2, I do have two vectors, and you can perform a variety of operations on these two vectors. In this case, what I want is essentially the dot product, and that's what this will tell us. And then notice I'm going to change the order and see if that makes a difference, and do that right there. So when I do v times w, all it tells me to do is take the a's, 2 times 5, and then add that to the b's, so it would be negative 3 times 3. And that's pretty much it. So I get 10 plus negative 9. And so, of course, I get an answer of 1. I'll go ahead and box that up. And there's your answer. So again, when you do the dot product, as you can see, it produces just a numerical value. In this case, you just get 1. Well, what would happen, everyone, if I did W times V? Well, same scenario. This would be my first, I guess, and this would be my second, but everybody wouldn't it basically be the same thing? So you would do 5 times 2, and then plus 3 times negative 3. And notice, of course, you end up getting 1 as the answer. So when we have two vectors, just long story short with this, and then we can move on, when we have two vectors, it says, is the dot product of those two vectors commutative? Meaning, does the order matter in which we place them? No. So in this case, of course, it is commutative. V times W is the same as W times V. Just like real number multiplication. Okay, nice. Well, let's go ahead on to the next piece here and get into a little trig. So the primary usage for us at this stage is to kind of talk about just having two vectors represented algebraically and determining the angle in between those two vectors. And so let's go ahead and put that piece in. And so here's what I have, everyone. Let V and W be two, and I have to kind of put this in, although we kind of knew this implicitly, but two non-zero vectors, because we can actually have 0 vectors there, but that's not for this purpose. So let V and W be two non-zero vectors, and then theta is going to be the smallest non-negative angle between them. So it could be acute, could be obtuse, and you'll see this momentarily, but this has to be in place for us to kind of go forward. So theta is the smallest non-negative angle between them. All right, and we're going to get a little formula with this, and here's our connection to the trig. So that theta is all based on that beautiful inverse cosine. And the reason I like that cosine is because if you remember, and this is a good connection to way back when, but basically when you do an inverse cosine on a value, you can either get a number between 0 and 90 degrees, acute of course, or you can do an inverse cosine and the calculator would give you the obtuse. So you can get an angle between 90 and 180. So this we don't have to play games with. The formula is as straightforward as it gets. So we're going to do inverse cosine, and then a couple things that we've seen before. Now here comes your dot product. So the dot product would be the numerator of our ratio. And then here's what's kind of interesting. The magnitudes show up. And so the product of the magnitudes would be the denominator of your ratio. So throw that in place if you don't mind, and then obviously we'll check it out with an example here momentarily. All right, so theta is equal to the inverse cosine of this ratio, and the ratio is broken up into two parts. Dot product makes up the top, and the product of the magnitudes makes up the bottom. Okay, well, let's try it out. So example 3 is going to do exactly what we want here. It says find the angle in between U and V. And let's go ahead and do this. Now remember, what's kind of interesting about this piece is you can start and stop essentially anywhere on the coordinate plane when we have this algebraic representation of a vector. So all it says is from your starting point, go 4 right and 3 down. But it doesn't say we have to start at the origin. I'm going to do that just because it's the easiest place for us to start. So let's go ahead and get U in place. And U would be 1, 2, 3, 4 to the right, 1, 2, 3 down, and then I stop. And so it's from here to here. Okay? All right, now, same with the V. In this case, I could have put the 2i and 5j anywhere. But if I want to talk about an angle in between two vectors, I believe it benefits us to kind of start this at the exact same point. So what I'm going to do, everybody, is from the origin, I'm going to go 2 to the right and 5 up. 1, 2, 3, 4, 5. And there would be my spot. And so that would be this vector right in here. And notice essentially when I have those two rays, for lack of a better description, I have essentially two angles, don't I? I have this one right in here, sort of right in those two, but I also have this one out here. And so that's where, if you remember in the description, theta is the smallest non-negative angle between them. So when I do my formula here, it's going to give me this one in the rotation, from here to here essentially, positive. Not from here to here. That's too large. Okay, you can kind of ballpark this. I'm just kind of looking at it here. I don't know, it looks not like a right angle, but fairly close. So it wouldn't shock me if we got an angle somewhere around 90 degrees there, but I don't think it's exactly a right angle, so probably not exactly. Okay, well, let's go ahead and see. In order to pull this off, everybody, we need three things. We need the dot product, we need the magnitude on U, and we need the magnitude on V. So in order for us to kind of move forward with this piece, we need those three pieces. All right, so let's do dot product first. And so remember, very simply multiply the A's and then multiply the B's. Oops. So something like that should be fine. And in this case, let's see what we end up getting. I have an 8 and a negative 15. I'm getting negative 7 as an answer. All right, so I hope everyone's okay with that. Dot product, multiplied the A's, multiplied the B's, and combine them together with addition. All right, now, good one right here. Let's go ahead and find a magnitude. So this would be, if you remember how to do a magnitude, 4 squared, negative 3 squared. So I have a 16 and 9. 16 and 9 is 25, and not too bad. This works out to be a perfect integer there. And you know that 3, 4, 5 Pythagorean triple. So 3 squared and 4 squared gives us the 5 squared. Perfect. Okay. Now, next one there, I've got to find a magnitude on vector v. How about a 2 squared and 5 squared? Well, 2 squared is 4. 5 squared is 25. 4 and 25 gives me 29. So I'm going to go with the root 29 on that. All right, well, the good news is we have everything in place. It's just a matter now of letting the calculator do the work. So let's go ahead and write our theta equals. And so it's going to be an inverse cosine. You just have to be careful of one thing with this formula. It's really not a bad formula to work with. Again, we kind of did most of the work already. But just when we have a product in the denominator, calculator is very picky on that. So it's those two multiplied together. You kind of do need parentheses around that piece. So I would type it in exactly as you see it on your screen. So inverse cosine, negative 7 divided by, and then the product of these two in the denominator. All right, well, I'm going to go ahead and bring my calculator up. And let's see, I'm going to clear a couple things here. In fact, I'm going to change a couple things that I have already up here. And by the way, go to your mode button, go to degrees if you don't mind. I think that would probably benefit us, as I do want this angle in degrees. And when you're ready, head on back and let's do it. So I have inverse cosine, and it will be negative 7 divided by, and as I mentioned, what you want to do is the denominator has to be in parentheses. So 5, and then times square root of 29. Just make sure we close all this off. Looks like I've got that. And probably one more for good measure. So something along those lines should work. Everybody, when you hit it, you get about 105. So in this case, it looked like we had a negative cosine ratio. And remember, cosine is negative in the second quadrant, and that's where that's defined for the inverse on that cosine. And so I had said it was somewhere around a little over 90 degrees. As you can see, about 105. That's what it turned out to be. Okay, so guys, let's put that in. Theta is equal to 105 and about 0.07 degrees. So in this case, that's this angle right in there. I'm going to tuck it in just for kicks. There's your angle. Okay, very good. So the last two components of this will just be talking about vectors that are parallel and perpendicular, essentially. So let's start with the parallel piece here. And on your paper it says two vectors. Let's go ahead and change that. Two vectors are parallel if, and here's what I have. The angle between them, and it's all going to be based on that angle, so we'll be using that formula again. If the angle between them is either 0 degrees or 180 degrees. This is going to be interesting. I'm going to have to kind of show you that visually in just a second. And I guess here's what I have on my paper. If the angle between them is 0 degrees, then the vectors point in the same direction. So just write it down, and then I'll kind of try to convince you with this visually. On your paper, I think it says something about a sketch there, so I'll do that momentarily. But it says if theta equals 0 degrees, the vectors point in the same direction. And if theta equals 180 degrees, as we will see momentarily, so if theta equals that, then the vectors point in opposite directions. All right, so what the heck does that mean? Let's go ahead and see it in action. I'll try to do both variations, and just so you can catch it. So I'm going to go ahead right about here, just kind of put a little vertical curtain in between the two. And here's how I guess I would say it. On the left-hand side, I'm going to do theta equals 0 degrees, something like that. And then on the right-hand side, why don't I try to tuck in, if I can, theta being equal to 180 degrees. All right, now basically what this would look like is if you have two vectors where the angle between them is 0 degrees. That's what's kind of interesting about this. Let's go with this. So here's one vector. And then the second vector, if the angle between them is 0 degrees, that means it's sitting right on top, right? It would look something like that. Two vectors, the angle between them is 0 degrees. Well, I know what you're saying is how, of course, can that be parallel? They're sitting one on top of the other there. And I guess the way I would describe it is, remember with vectors, you can place them wherever you want, and they're defined algebraically the exact same way. So the starting and stopping point are arbitrary. So for example, in this case, by putting the vertices in the same spot, you see the angle is 0 degrees. But if I don't put the vertices in the same spot, then as you can see, they're two vectors that are parallel. They're going in the same direction, and they don't touch. So that's sort of the way around this piece right here. These two are parallel. And if I put them together and did my angle between them, they would be 0 degrees. Same thing on this. Let's go ahead and do the 180. So this would be opposite directions. So something like this on this end and this on this end. So there's 180 degrees, by the way. Let's see if I can get that in. There's 180 degrees between the two vectors. Again, having the same initial point right there, of course. And I know, again, you're kind of saying to yourself, well, those aren't parallel at this point because they're touching right there at the initial point. But, again, that part is arbitrary. So if I start from there to there, in this case, how about if I just move that one, kind of translate it down, now you can see they're pretty much, they're parallel. Okay, and so by touching them, you see the angle is 180 degrees between them, but in essence, they're parallel, and they're going in opposite directions. Hope that description helps just on that piece. We'll go ahead and just do an example to check that out momentarily and go on to the next. So everyone, example 4 on your paper, it just says determine whether the vectors are parallel. So all we need to know is the angle between them. Is the angle 0 degrees or is the angle 180 degrees? If it is, parallel. If not, not parallel. All right, so let's go for it. One more time. I need dot product. I need magnitude on V. And I need magnitude on W. So let's go ahead and get this together, everyone. Dot product now is probably the third or fourth time looking at it. So I have 3 times 6, and then plus in the middle, everyone. How about -1 times -2? So it looks like I have 18 and 2. I'm getting a 20 on that one, everybody. All right, perfect. Now guys, let's go ahead and do a magnitude on this. So magnitude would be 3 squared and negative 1 squared. And when I do 9 and 1 added together, it gives me 10. So I'm getting a magnitude of square root of 10 on that. Last one here, everybody. Let's get this taken care of. Looks like I have 6 squared and negative 2 squared. How about a 36 and a 4, everybody? 36 and the 4 would give me 40. And so I'm thinking this would be square root of 40. Now, just kind of working it out here, let's see if we can do this together. Here's what's kind of interesting. The top sort of speaks for it. Oh, actually, I missed one thing there. Let's do that inverse cosine, of course. So theta is equal to the inverse cosine. 20 is our top. And then officially, the bottom would read root 10 times root 40. Let's see if we can do something about that. And let's see if we can do this maybe without the graphing calculator. Curious if I can refresh your memories on a couple things here. So here's what I have. Inverse cosine. That 20 is not moving at all right at this point. But how about that bottom, everyone? Root 10 times root 40 is really root 400. And the square root of 400, as a matter of fact, if you were to do it, is 20. And so you end up getting here the inverse cosine of 1. And you have seen this before, of course. You're asking yourself what angle has a cosine ratio of positive 1. And within our interval, everybody, that angle happens to be 0 degrees. If you were to do inverse cosine of 1, I'm going to go ahead and bring it up just in case you're not convinced. Inverse cosine of 1, of course, is 0. And so as a result, determine whether the vectors are parallel, and the answer has to be yes, indeed. You're more than welcome to kind of graph that on the coordinate plane and kind of see for yourself there. But I think if you graph those, you would see that they are just two vectors that point in the exact same direction. Again, I'll leave that up to you at this stage. Last piece, everyone, is to take a look and see if two vectors are what are called orthogonal. Orthogonal is just another word in this context for perpendicular. And so here's what's kind of interesting about this piece. It's obviously, guys, if they're perpendicular, the angle between them is going to be 90 degrees. But I think we can simplify this, and I'm curious if you're going to be able to kind of pull this off. All I need to know, actually, is if their dot product is 0. So I'm able to shortchange the formula a little bit on the perpendicular here, on what's called the orthogonal. Because if their dot product is 0, then right away I know that the two vectors are orthogonal. And it says it on your paper, what does that mean? Why? Why is it that simple? So let's go ahead and kind of figure this out for just a second. And here's, I guess, what I would say. It says, what does that mean in terms of the dot product of two vectors? Use the formula for the angle between the two vectors. So everyone, here's the angle between the two vectors. I do the inverse cosine, and then I do, let me do the bottom first, magnitudes down on the bottom. And then in this case, it basically says if the dot product is 0. So the dot product makes up the numerator of our ratio right here. And so here's the great one. In this case, if the dot product is 0, hey everyone, what is 0 divided by anything down here? Well, 0 divided by anything is still 0. And no matter what, of course, what is the inverse cosine of 0? Well, we've seen this before. The inverse cosine of 0 is 90 degrees. And again, if you've forgotten all that stuff about inverses, let's just quickly pull that off up here. So inverse cosine, 0 divided by anything is 0. And inverse cosine of 0 is 90. So as it says on your sheet now, you can totally shortchange this when I ask for perpendicular or orthogonal, is if the dot product is 0, yeah. If not, no. So last one here, example 5. Determine whether the vectors are orthogonal, meaning is the angle between them 90 degrees? Well, very simply, all I have to do is the dot product. So let's see what V times W is. I don't have to worry about magnitudes. I don't have to worry about inverse cosine on that because of the way I described it up above. So here we go. 2 times 6 plus 3 times negative 4. And it looks like 12 plus negative 12, and that is definitely 0. And so the answer is yes. If you were to do the inverse cosine, if you were to use that formula for the angle between two vectors, of course, you're going to get 90 degrees. All right, good. So some nice connections here with just working with one of the operations on vectors, and then, of course, kind of dealing with the trigonometry. In this case, it's with the cosine ratio. All right, everyone, if you just have some questions on this, please don't hesitate to ask, and I'll be available for assistance. Thanks for listening, of course, as usual.